Okay, very good. We can see it, just put it in full screen mode and then you can start. Go ahead.
All right, thanks to the organizers for the invitation to talk about my work. And what I'll talk about today is some recent work on computing Bottomonium suppression in the quark-gluon plasma and also elliptic flow using real-time quantum evolution. And during the course of the talk, I'll explain what I mean by that. The talk collects together 3 papers. 2 are sort of related, and then the second one is forthcoming. This work was funded by the Department of Energy and also by folks at the TU in Munich. All right, so our basic picture of quarkonium suppression in the quark-gluon plasma is that if we look at the vacuum potential, we'll see something akin to a Cornell potential. And then if we measure on the lattice, what happens is we jack up the temperature, we'll see that essentially a melting of this potential, and then states will eventually become unbound. This is due to 2 things: one, screening in this sort of medium range distance, but also the string melting at large r. Now, one thing that this picture misses when you just plot the real part of the free energy as a function of r is it misses the fact that there's also, you could think of this sort of as the potential between the 2 quarks, but if you just look at the real part, you're missing part of the information. In the medium, the states have a finite width, which can be quite large, on the order of tens to hundreds MeV. And that information is encoded not in this quantity, but in the imaginary part of the potential. And that is related to the fact that we have these larger spectral widths of states in the thermal medium. So below is showing, what we expect to see, or what we actually see from experiment in PP collisions, where we can clearly identify an upsilon 1s, 2s, and 3s. And the expectation is that as we increase the temperature, what we should see is that the number of these states decreases, but also that if we could measure the in medium spectral function, we would see that it was getting wider and wider as we jacked up to the temperature, and to the point that this state sort of ceases to exist at some point. And this is our sort of modern understanding of this process. And these spectral widths result in medium breakup of these states. So, and these widths are large even before you hit the official dissociation point of the state. So even at temperatures lower than the dissociation point, these states are breaking up in the medium. So this has to be taken into account. Now, in terms of the data, what I show here is on the left, again, upsilon 1s, 2s, and 3s. And the red dashed line is is the production in PP. No, that's RP lead. The blue is the PP data. And then on the right, we can now compare that PP data, which is the blue, is the red here. And then the RAA for the states is this down here. So we can see that from this data in the lead-lead collision, the upsilon 3s is completely disappeared. The upsilon 2s is strongly suppressed. And there's even some relatively strong suppression of the 1s from the data. So how do we want to deal with this conceptually? So what we're going to imagine is, since we can work in sort of heavy quark effective theory, or PNRQCD if you like, that we can reduce this problem down to a Schrodinger equation in which we have some effective state that's in some potential linear combination coming in. It has to propagate through the quark-gluon plasma, and then there are different overlaps on the away side, and the magnitude amplitude squared of this one versus this one tells us the amount by which the state was suppressed during its propagation through the quark-gluon plasma. One can alternatively think of this in terms of density matrices, so that I have some probability to be in this particular state in the incoming state, and then I want to evolve the density matrix and get the outgoing density matrix and get the probabilities that I find them after the propagation through the quark-gluon plasma. because bottomonium states have a quite large binding energy, that means that they're formed at times less than on the order of 1 fermi over C in the lifetime of the quark-gluon plasma. For the 1s, the estimate of the formation time is on the order of 0.2 fermi over C. And then they propagate through the plasma. The plasma lifetime in the highest energy LHC collisions is on the order of 10 to 15 fermi over C for mid-central collisions. So they experience a kind of long lifetime inside of the plasma. Now, during their long life in the plasma, these states can break up and potentially reform due to in-medium transitions induced by gluon absorption and emission. So we need to somehow have a way to take into account this at a kind of microscopic level. Now, this is complicated by the fact that instead of having just a brick of QGP that we can shoot our bottomonium states through, these states live in a now evolving medium. We can sample the initial production points of the bottomonium states. They're correlated with the initial energy density deposited in the quark-gluon plasma, but of course they don't stay fixed. They start flying around. In this case, I show 200 sampled trajectories. But while they're flying around, also the background is changing, the temperature is decreasing, and the plasma is expanding. So the way we sample the momentum is just to use essentially known information from PP experiments to get the initial PT distribution in the lead-lead collision. Now, to do this systematically, what we're going to use is something called an open quantum system approach, in which we treat the bottomonium state that's propagating through the quark-gluon plasma as some probe, which is a subsystem of our full quantum system. The full quantum system also includes the medium, which is this quark-gluon plasma. The medium includes all the light quarks and gluons that we assume are, in near perfect thermal equilibrium or close to it, and that's the stuff that we call the quark-gluon plasma. And then what we want to do is take the total Hamiltonian operator and then split it into 2 pieces, one which explicitly only involves the probe, one that involves the medium Hamiltonian, and then some potential interaction terms between medium and probe. And at least in the heavy quark limit and small coupling limit, we can treat this H-int here perturbatively. Now, if we were describing the total density matrix of the system, which is, at least for a thermal ensemble, constructed from the following, it would, of course, obey the following kind of evolution equation, which tells us that we preserve unitarity in the trace of the density matrix. And at the Schrodinger equation level, this would just reduce down to the normal Schrodinger evolution for the total system. If instead we're only interested in the dynamics of the probe, what we can do then is trace out the medium parts and construct what's called the reduced density matrix. And then the question becomes, if I trace out all of the medium degrees of freedom, what is the appropriate evolution for this reduced density matrix? Is it different than this one? And the answer is yes, but we have a few steps to get there. In order to get to the sort of effective evolution equation for our reduced density matrix, we have to also consider the various timescales at play here. There's a relaxation time for the medium itself, which can be expressed in terms of some correlation function between medium operators, and one expects that this should decay exponentially with some given time. And there's also what's called the intrinsic probe scale, and this is related to the difference of energy levels in the system that's doing the probing, and how fast do transitions between those two things occur. And then finally, the probe relaxation time itself. Now, in the limit that the probe relaxation time and timescales are much, this should say much shorter, sorry, there's a typo there, than the medium relaxation time. So sorry, they're much greater. So the medium, that's right. So the medium relaxes much faster than the rest of the guys. then you can formally show that the evolution equation for the reduced density matrix can be expressed in the following form. And this is referred to now as the Lindblad equation. In this Lindblad equation, H probe is a Hermitian operator, and these operators Cn here are called collapse or jump operators, depending on the paper that you read. They are related to the partial and total decay widths of the state as, that exists in the probe. So the partial decay width can be obtained by this product of these jump operators, and the total decay width is simply the sum over all of these partial decay widths. It turns out that an efficient way to reorganize this is to, instead of writing things in terms of this Hermitian operator H probe that's up here, it's better to write it in terms of some effective operator, so we can see what's going on in the physics, which is H probe minus this instantaneous, well, the total decay width, right? So what's happening now is we've pulled in some part of this, of the decay into the Hamiltonian, and now this thing is non-Hermitian. If you rewrite the top equation in this way, what you'll find is the following evolution equation for the reduced density matrix. The first part is sort of what you would expect. It's kind of that commutator term, but now with a Hamiltonian that's not necessarily Hermitian. In this case, it's explicitly non-Hermitian. And then there's another term, which is just the probe density matrix itself sandwiched between two jump operators. So in a paper, it's a couple of papers that came out in 2016 and 2017, Nora Brambilla, Miguel Escobedo, Jon Soda, and Antonio Vario did the calculation in potential non-relativistic QED of these jump or collapse operators. And here they are explicitly, if you're interested. What these collapse operators do for you in practice is they allow you to transition between, in this case, different color states, between singlet and octet through gluon absorption or emission the other way, and octet singlet and octet transitions. You can factorize the total density matrix into two blocks, essentially, which are the singlet part and the octet part of the density matrix. And then as a result, you can then, and you can also write down this effective Hamiltonian that's appearing up there with some singlet and octet parts, some real part, which comes from in media modifications.
It's just fantastic. Like, Cassie suggested.
Hey, Rob. And we can also write down an analytic expression for the total decay width here. These coefficients that appear in the real and the imaginary parts can be written entirely in terms of correlation functions, in this case of chromoelectric fields with one another, the real and the imaginary parts of those correlations, and these can be extracted directly from lattice data in principle. Now, you can, if you want to solve this thing, the first thing you might think of is then further decomposing the singlet and the octet parts of the density matrix using some angular momentum basis. And then you could truncate that angular momentum basis with some maximum L, and then reduce it to a lower dimensional problem. To then solve it on a computer, and that's what was done in the second of these two papers, you could then discretize the wave function with some specific number of grid points, and then evolve the full reduced density matrix. But if you do the counting in this case, what you find out is to solve this problem, you then have to evolve matrices that can be quite large. And in our case, for the simulations, this num here can be thousands. So that's the downside of this approach. Although it's nice, you can reduce it down to finite matrices and then evolve the full density matrix. The computational side of it becomes very difficult. It's it's not straightforward to parallelize such an algorithm. The approach that we followed in the paper that's coming out soon is to instead follow something that was in the open quantum systems literature, which is called the quantum trajectories approach. And in this approach, you treat this final term essentially stochastically, right? So what we're going to do is we're going to evolve the system with this non-Hermitian Hamiltonian, and then with a well-defined set of rules, we apply these jump operators. As a result, you can reduce this whole problem now to solving a one-dimensional Schrodinger equation with this non-Hermitian Hamiltonian, and then stochastically sampling these quantum jumps. And as I said before, the quantum jumps encode all possible transitions between color and angular momentum states, and they're automatically subject to whatever selection rules are appropriate. So we reduced the problem to this for each physical trajectory. That's my Bottomonium shooting its path through the quark and plasma. We can then solve the Lin-Ballard equation by averaging over a large set of independent quantum trajectories. And the payoff from this is that it's instantly parallelizable, and the machines don't even have to talk to one another. Another advantage of doing it this way is that we don't have to introduce any angular momentum cutoffs into the calculation, and the algorithm scales very nicely. So what we have found in practice is that the full evolution turns out to be very, very well approximated by the leading order evolution, at least for the ground state. And I'll show you some evidence of that in a second. And then when we turn on this jump term, we see that the jump corrections affect the suppression of the excited states more than the ground state. On the left, I just sort of showed you a pretty picture of what it looks like, when we make color transitions and angular momentum. These are the angular momentum split lines here. This is a singlet octet, and I can make all sorts of transitions here, including ones that might, if I started out in a singlet, I might make a round trip and come back to singlet. So that's the kind of things that we're trying to take into account when we have this term turned on. When this term is not turned on, essentially you just lose through all possible channels, and you don't have anything coming back to the ground state. So in some sense, you can think of this as being the source of the quantum regeneration of the state. So first, I want to show you some results from the Nojump evolution. And that was released in a paper by my student, Agrahul Islam, here at Kent State, and myself. And what we did there was we sampled roughly 3.6 million physical trajectories in different impact parameters. This is what one of the initially sampled guys might look like. And then we turned on this simulation to let them fly, and we recorded the temperature along each of these paths, and then for each trajectory, solved the real-time Schrodinger equation with this complex potential. For the background, we used a realistic 3+1 dimensional hydro code called a hydro, and we're only interested so far in the L is equal to 0 and L equal to 1 states. And when you don't have jumps turned on, these you can just simulate them independently. The survival probability that we are going to extract is this quantum mechanical ratio of the overlap of some vacuum state indexed by N and L with the wave function that was evolved through the simulation. And then we compare that to the overlap that was in the initial condition. Now, of course, if we're going to do real-time evolution, we have to have some initial wave function that we're going to shoot through the system. And here we take advantage of the fact that in the heavy quark limit, the production is local. In the infinite M limit, it's strictly a delta function. But when M is finite, there will be some width to this. And also for numerical reasons, it's hard to put a delta function on the lattice. We start with essentially a smeared delta function in the form of a Gaussian. And this parameter delta that's chosen here is just chosen small enough that it agrees when we do the evolution with a real delta function to a part in 10 to the minus 4 or something. But the real delta function is numerically super expensive, so for that reason we use the smeared one. And then for the no-jump case, what I'm going to show you is 3 different times where we turn on the medium, essentially. And I'll also show you some other variations in the model. Right? Because of this initial condition, the system is not in a given state in the before it flies through the plasma. It's in a quantum superposition. Right, after shooting them through the plasma and then extracting their survival probabilities, we can then do that for as a function of the impact parameter of the heavy ion collisions. Over here on the right is a central collision, and on the left is a peripheral collision, and then we computed along all here the survival probability. The black lines that are going through here are the central values of the parameters that we chose. The parameters that we had to play with were when do we turn on the medium evolution and medium effects on the Bottomonium states themselves, and also the in-medium Debye mass, which we varied by 50% around the leading order PQCD value. The bands show those variations, and the line is the central one. This is as a function of Npart, and this is as a function of PT on the right. The little dip that you see down here can be explained in the model by the fact that slow-moving particles have a longer effective lifetime in the plasma, and so therefore are suppressed. From this RAA calculation, we can also try to gain some intuition into where this suppression is occurring and where are the states escaping from. This on the left is showing for 1s production, where did the states start to receive their final RAA. So we can see the ones that had very little suppression tend to start here on the outside of the system, and those that had the strongest suppression were those that were born in the center of the quark-gluon plasma. And this pattern holds up for all of them. Now, I don't know how this is useful for for experiment, but it's nice to see that it lines up with our expectations. Now, in addition to RAA, there's been some there are now measurements of the elliptic flow of the upsilon 1s. I don't know if you necessarily would call it elliptic flow, because what it really is differential or anisotropic suppression. If we have a non-central collision, then these states that fly, it's expected that states that fly out along the short side would experience less suppression than those that fly out along the long side. Turns out that this can be complicated by the expansion of the plasma itself, because in such a case, what happens is the quark-gluon plasma itself expands more rapidly along the short side than on the long side. And as a result, it can overtake some of these states that were flying out of the plasma. This turns out to result in a prediction, at least for low momentum particles that can get swallowed by the quark-gluon plasma, that there should be a negative V2. And if you turn off the transverse expansion, you find that this is perfectly finite. So we have a kind of prediction here that by measuring a negative V2 here, we can gain information also about the velocity of expansion of the quark-gluon plasma itself. Now, in this paper, we attempted to bin everything for the elliptic flow in exactly the bins used by the experiment. The little boxes are systematic error that comes from varying those turn-on times and the Debye mass itself. In some cases, that's quite small and under control. For the elliptic flow of the excited states, the 2s and the 3s, we can see that there's a larger systematic uncertainty, but it's not terrible. We also went through the exercise of comparing with an old, what's called adiabatic approximation calculation. This is for the elliptic flow again. And this is that dip that I was showing you before. The dots are the results of our 3.6 million quantum trajectories, and the black is an earlier paper that did it in what's called the adiabatic approximation. It still involves a complex Hamiltonian, but you don't do the real-time evolution. You just you do something simpler. Now, for the second part, which will be a little bit shorter, given that it has no introduction, we already did the introduction, is about this forthcoming paper with the Munich crew. And I'll just skip to the final plots that we've thus far generated, which on the left is RAA, again, versus Npart, for the 1s, the 2s, and the 3s. The world data is collected here on the plot. The variation in this case is varying that, that in-medium transport coefficient, if you like, kappa hat, between some bounds, which are obtained from lattice data, and holding that other one, gamma, which represents the real modification of the potential fixed. On the right, we show the same thing, but now holding kappa fixed and varying gamma around. And we see that there's a largest sensitivity to the assumed value of gamma. So this motivates pushing lattice calculations of this to try to find out what the true value of gamma. I would say that most recent ones seem to be hinting that it's over here in the region somewhere close to 0. But overall, we see quite reasonable agreement with the data. Based on that, we can also make predictions for these what are called double ratios. So this is the upsilon 2s to 1s in lead-lead divided by the same ratio in pp. And again, on the left is varying kappa, and the right is varying gamma. And here, because some of the systematic theoretical uncertainties cancel out, we have a more tightly constrained result. It's nice to see that this depends more on gamma over here, because maybe in the future, as more statistics come in, we can also try to get some kind of indication of gamma from experiment itself. The top was the 2s to 1s, the bottom is the 3s to 1s. And once again, we see reasonable agreement with the data. Now there's a caveat here. The CMS here only has upper bounds on this quantity, because it's almost completely destroyed in the plasma. It's hard to get enough statistics to do this, at least when the results were produced. The ATLAS results, again, for the same reason of limited statistics, don't do the 3s directly, but they make an estimate of this ratio from the 2s plus the 3s. So the top one's solid, the bottom one it's suggestive, but I wouldn't say that it's the cord is out on this one. Now, to finally summarize the short second part of the talk, we can now look at what do these jumps effectively change. So what I've done is I've collected here the solid lines are the case with the jumps, and the dashed lines are the case without jumps. So the second part and the first part of the presentation. And the various panels are varying kappa on the top and varying gamma on the bottom. And our sort of, default model is sitting here. And as I advertised in the beginning of the talk, what we find is that for the 1s, for the ground state, these things are quite small. But what we see is when we turn on the jumps, we see enhancements in the excited states. And these enhancements are important, in particular for the 2s, of landing you in the right ballpark of the observed 2s to 1s ratio. All right, so that's it for my main slides.
Michael, I suggest that since you have already spoken 30 minutes, maybe we can jump to the questions and leave the slide with the conclusions on the screen.
Okay, no problem.
Okay, so let me ask if there are any questions to this nice talk. Peter, go ahead.
Hi, so in the diagonal evolution without the jumps, you said you're using a complex potential. So what is that complex potential that you're using?
Yeah, so the complex potential that was used in the Nojump case, where it was trying to get to the result to produce this plot, was the same one that I used. It's the KSU potential, which is this, it's a just a Debye screened KMS potential, essentially. That's all it is, with an imaginary part that's given by the Lina calculation.
And the real part?
And the real part is this Debye screen, is the KMS potential.
Oh, so the Debye screen, so it's strong screening.
Yeah.
Okay.
It's the internal, actually it's the internal energy from the KMS, right? So it's the same thing that we've been using for at KSU for the last 10 years. I didn't want to switch that when we switched from adiabatic to the real-time evolution, because I wanted to be able to, you know, at least hold one thing fixed. In the jump evolution, there we're using the potentials that came from the, whoops, I went the wrong way. In the jump case, we're using the potentials that came from the PNR-QCD calculation.
Yeah, but what I'm saying that you're worried about kappa and gamma, but the potential is also a big elephant in the room.
Right. Well, the hope is that with the second part, we can get rid of using the internal energy KMS stuff. So the hope is that we can just use these kind of simple potentials that come from the PNR-QCD analysis that have kappa and gamma in them. And then after tuning these guys to, let's hope, lattice data, then this degree of freedom will be removed. That's the hope.
Okay, let's move to the next question. Petrov.
Hello, thank you very much for your talk. In your talk, you have mentioned at least 3 relaxation times. What can you say about possibility to have some information about these relaxation times from experimental data, or they have some inherent theoretical definition?
Right. Yeah. So it's my understanding that, of course, in this particular ordering of the timescales, you can get to a Lindblad equation. If you have different ordering of these timescales, the system can become non-Markovian, and you reduce the system to something that's called a master equation. You can still write down an evolution equation, but it's much more complicated. And there are efforts to try to look at these more general master equations. Now, the only practical way I would know to do it would be try to evolve it, try to make a different assumption, right? That the scales were in a different order, and then take the resulting master equation, which emerges or whatever it is, and then try to compare it to the data as well. Other than that, I don't know how to fundamentally measure these relaxation timescales. Perhaps it could be done on the lattice. I don't know.
Okay, thank you.
One possibility.
Thank you. Clear. Thank you.
Okay, thank you very much to everyone. Let's move on to the next